So how can you provide the test bench here? Like it's just like okay.
It's a good question. So I guess the first answer to that is since transaction level Verilog is an extension of system Verilog, any test bench infrastructure that you want to create in system Verilog, you can create. It's one of the main limitations of the current MakerChip platform is your design is entirely in a single file. So at this point it's meant for smallish designs. Although I was able to do the Warp 5 design in a single file without too much trouble. Nonetheless, so if you want to have a separate module defining your test bench that wraps your main design under test that's written in transaction level Verilog, you would do that all in the same file.
Okay.
And you can also just use transaction level Verilog for providing your test bench behavior.
Yeah. So what is it here? The assert these two end simulation. I couldn't understand what is the like passed and failed.
Yeah, so I can explain that now. Yeah, okay. I'm just trying to think of what's coming up in the presentation. So these two signals are defined on the interface of the module that we're defining as signals that feed back into the infrastructure to control the simulation. So if we assert, if the passed signal is asserted, that will end the simulation with a passed message in the log. So if we look over at our log file, we're going to see a passed indication because this is set to just pass after 40 cycles, regardless of what's happening. And then failed, you can assert to indicate failure, and we would get a failure message instead of a pass message. So this is your ability to control the simulation. Make sense?
Yeah.
All right, so you guys can try out this part on your own. So I've done a simple inverter. You guys can try out other expressions and view the waveforms. Okay, I'm going to move on pretty soon, so if anybody's having trouble, let me know.
Yeah, I don't see the waveform. I don't see in one. I simulated, but I am not seeing in one.
And what's your expression?
Out is not equal to in one.
I'd have to debug that one offline, I guess. I don't know why that would be.
So Pravesh, you can send that link to us in the chat box.
No,
so not equals or equals not?
Yeah, before sending that link, I need to save, right?
It's save your project.
Save project, okay.
So one thing it might be is you can shrink this down, which would hide your signals. Other than that, I'm not sure.
Dan, you were saying something?
Oh, he said not equals instead of equals, like not in. Is that valid?
Yeah, Pravashi, Dan was checking whether it should be equal and not equal, the other way around.
It's equal, not only.
Okay. Yeah, we'll try it offline.
Okay.
But it's not going to hold you up for future experiments.
So I think we should continue with the presentation.
Yep. So next we'll try some vector operations, some arithmetic operations. So just like in System Verilog, except the assignment statement itself is acting as the declaration. So we provide the type of the signal where we're providing the assignment. So you can do a line like this to do an addition of 4-bit wide numbers to produce a 5-bit wide number. And you can go ahead and do this. I'll do it as well. You can actually cut and paste from the slides.
So somebody had a question about the bus declaration, right? This is how you do it actually.
here.
Yes. Yep. And I'll go ahead and compile. And while you're trying that, I'll take a look at my site and see how busy it is. Well, we got a couple little blips, but we're going to have to work harder to stress out my server. All right. So hopefully you've been able to compile that line and get a waveform. On my waveform, I see that, let me get my spotlight. I see that 0 plus F is F, 9 plus 8 in hexadecimal apparently is 11, and so on.
Anyone has any questions on this one, or should we, anyone trying out this code?
Yeah, it's
Steve,
fine.
how do we get to
Yep.
know about the coverage? Like we are going through whether, is there any way to see the coverage? Like the stimulus are random, right?
The stimulus is random. There's no built-in mechanism today for automatically generating coverage reports or anything like that at this point.
Okay, yeah. Yeah, that would be better actually. If we are missing something, we can just add those stimulus and we can compile it.
Mm-hmm. Yep. Yeah, there's definitely opportunity for working in some coverage capabilities. All right, so I'm going to move on to sequential logic. So this example here is a little bit of logic that's computing the Fibonacci series. So the Fibonacci series, in the Fibonacci series, every number in the series is the sum of the previous two numbers. So we start off with two ones. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, etc. So representing that in hardware, every cycle, our next number is going to be the sum of the previous two numbers. And so this is our circuit. We're using flip-flops. I'm assuming that everybody's been exposed to flip-flops. So a flip-flop is essentially taking, blocking the input value until the clock edge, at which point it captures the input value and drives that value as output for the next cycle. So by setting up this sequence of flip-flops, each cycle, these values are going to shift to the right by 1.
Steve, can you turn on the pointer?
Yeah, sorry. Yep. So this is the sequence of values that might be in the machine at a given time, and on the next clock, these are going to shift. And we can see that in the waveform. But there's a little missing piece to this, which is we did not consider reset. So we have to start the sequence off somewhere. The environment in MakerChip is going to provide you with a reset signal that we can see down here in our waveform. It starts off high and then drops low. So, you know, the idea of reset methodology is reset will be held for a large number of cycles, during which time you stabilize the state of your machine. Then reset drops low, or often reset is inverted, but here it's an active high reset. You drop reset low and allow your machine to start operating. So we need to reset to a sequence to at least 2 ones, and we're just going to use reset to hold the value at 1. And as soon as we release reset, we'll start counting 2, 3, 5. So we add in this reset mux. On reset, we will capture a value of 1. Otherwise, we'll start counting.